we are going to discuss the source conversion. In this particular topic, you guys will come to know how to convert a voltage source into a current source and a current source into a voltage source. So if you guys have a practical voltage source, with the help of this technique, you guys will be able to convert the voltage source into current source, and you guys will be able to convert the current source back into the voltage source. Let us consider the practical voltage source over here. Rs is the internal resistance of the voltage source, which is always in series with the voltage source. If the internal resistance of the source is 0, then this source will be known as ideal source. And under load condition, there will be no voltage drop across this resistance. As the internal resistance of this source is not equal to 0, this is why we call it a practical source. So what we want to do over here, we want to convert this practical voltage source into a practical current source. This is a practical current source. The current delivered by the source is Is, and the internal resistance of the current source is Rs. Rs is the internal resistance of the current source, and keep it in your mind that the internal resistance of the current source is connected in parallel with the current source. So the resistance is connected in parallel. If the resistance is equal to 0, then if the resistance is equal to infinity, then this current source will be known as an ideal current source. So the internal resistance of an ideal current source is infinity, while the internal resistance of the voltage source is 0. Now, in order to convert this voltage source into the current source, we need to calculate Is, and Is will be equal to Vs by Rs. So we can calculate Is with the help of this equation, and then we connect the resistance Rs in parallel with Is, and this becomes a practical current source. Let's say we guys have the current source and we want to convert it back into the voltage source. So in order to convert the current source back into the voltage source, we need to calculate Vs, and Vs will be equal to Is into Rs. So you guys need to calculate Vs. Once Vs is calculated, then the resistance Rs is connected in series with this Vs, and this becomes a practical voltage source. So with the help of this particular topic, you guys will be able to convert a practical voltage source into a practical current source, and a practical current source into a practical voltage source. Let me consider the circuit diagram of an ideal voltage source. So if we have an ideal voltage source, the internal resistance of the ideal voltage source will be 0. So this is the symbol of the ideal voltage source, the internal resistance of this ideal voltage source is 0. Let me draw the circuit diagram of the ideal current source. So this is an ideal current source, and the current delivered by this source is Is, and the internal resistance of this ideal current source is infinity. So you see, these are the symbols for the ideal voltage source and the ideal current source. Now let us talk about the charging of a capacitor. So we want to charge this capacitor with the help of this series resistor, and we charge this capacitor with the help of a DC voltage source. So we shall connect this DC voltage source across the series combination of the resistor and capacitor. We know that the capacitor blocks the DC current. So under normal condition or under steady state condition, the current in this circuit will be 0. But initially, this capacitor will withdraw some charging current. This charging current will be for a very small interval of time. We do not consider this state of the circuit, this charging state of the circuit under normal condition. Under the normal condition, we consider this particular condition only, that the capacitor behaves like an open circuit for the DC voltage and it blocks the DC current. But initially, this capacitor will be charged. It will withdraw some current from the source, and the charge on the plates of the capacitor will develop. Finally, the voltage across the capacitor will be equal to the source voltage. Anyhow, we have installed a switch in this particular circuit over here. We will connect the switch at time t is equal to 0, and while connecting the switch of this particular circuit at time t is equal to 0, we assume that there is no voltage across the capacitor. So this is the initial condition. Under the initial condition, we assume that there is no charge on the plates of the capacitor at time t is equal to 0. There is no voltage across the capacitor at time t is equal to 0. When we connect the switch of this particular circuit, there will be a flow of AC current. There will be a flow of time varying current in this series combination. We assume that the current is a time varying current. This is just an assumption. We will derive the equation for this current. If the current is changing with respect to time, then it will be a time varying current. If the equation for the current is in terms of time, then it will be time varying current. And if the equation for the current is a constant, then it will be a constant current. So anyhow, we assume that there is a time varying charging current in this RC series combination. And whenever there is a current in this particular circuit, there will be some voltage drop across the resistor as the current is changing with respect to time. So the voltage across the resistor will be changing with respect to time as well. And as the current is changing with respect to time, so the voltage across the capacitor will be changing with respect to time as well. So we apply KVL to this particular loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. The voltage across the source is a voltage rise because the current flows from the negative terminal of the source towards the positive terminal. The voltage across the resistor is a voltage drop because the current flows from the plus polarity of this voltage towards the minus polarity. Similarly, the voltage across the capacitor is a voltage drop. Why? Because the current flows from the plus polarity of Vc towards the minus polarity. So according to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. The only voltage rise in this loop is the voltage across the resistor, and is the voltage across the source. The voltage across the resistor is a voltage drop, and the voltage across the capacitor is a voltage drop. So we close the switch off this particular circuit at time t is equal to 0, and there is a charging current in this particular circuit. This charging current will result in a voltage drop across the resistor, which is represented by VR, and a time varying voltage drop across the capacitor, which is represented by Vc. So we apply KVL to the only loop of the given circuit, which states that the voltage across the source will be equal to voltage across the resistor plus voltage across the capacitor. Keep it in your mind that the voltage across the source is constant with respect to time. It is a DC voltage, while the voltage across the resistor is a time varying voltage. Similarly, the voltage across the capacitor is a time varying voltage. We know that the voltage across the resistor is equal to IR. We put this value in this particular equation. So the voltage across the source will be equal to IR plus Vc. Well, this is a series combination. This is a series current. The same current flows in the resistor, the same current flows in the capacitor, and the same current flows in the source as well. So as far as I is concerned, this is the current in the resistor, capacitor, and voltage source of the given circuit. So we know how to calculate the current in the capacitor. So the current in the capacitor is equal to C into dVc by dt. We put the value of this current in this particular equation. Vs is equal to IR plus Vc. So if we put the value of the current in this equation, we obtain this particular equation. That is, the voltage across the source will be equal to RC into dVc by dt plus Vc. And what we do, we rearrange this equation. So the rearrangement of this equation gives you the last equation of this particular slide, that is minus dVc by Vs minus Vc, which is equal to minus dt by Rc. Now what I do, I integrate both sides of the last equation of this particular slide. So we integrate both sides of this equation. We integrate the left hand side of this equation, and we integrate the right hand side of this equation. So we integrate both sides of this equation. The integration of the left hand side results in log of Vs minus Vc, and the integration of the right hand side results in minus t by Rc plus k, where k is the constant of integration. So we need to find out the constant of integration in this particular equation, and we can find out the constant of integration in this particular equation with the help of initial condition. And what is initial condition? We know that at time t is equal to 0, the voltage across the capacitor is 0. This condition is known as initial condition. So we find out the constant of integration with the help of initial condition, that is, at time t is equal to 0, the voltage across the capacitor was 0. We put this particular condition in this equation, and we calculate k. So let us put the initial condition in the last equation of this particular slide. So if we put the initial condition in the last equation of this particular slide, we get the value of the constant of integration, which is log of Vs. So we put the value of k in the given equation. So log of Vs minus Vc is equal to minus T by Rc plus log of Vs. We rearrange this equation. The rearrangement of this equation gives you log of Vs minus Vc by Vs, which is equal to minus T by Rc. And what we do, we calculate NT log on both sides of the last equation of this particular slide. We calculate the NT log on both sides of this particular equation. So NT logarithm on both side yields Vs minus Vc by Vs is equal to e raised to power minus T by Rc, and we simplify this equation for Vc. So the voltage across the capacitor will be equal to the voltage across the capacitor will be equal to Vs minus Vs into e raised to power minus T by Rc. And the same equation can be written as, there is no difference between the last two equations of this particular slide. The voltage across the capacitor is a time varying voltage. This is an instantaneous voltage, and the instantaneous expression for this voltage is Vs into 1 minus e raised to power minus T by Rc. So we will calculate the voltage across the capacitor with the help of this particular equation. We sketch the voltage across the capacitor with respect to time. So if we sketch the voltage across the capacitor with respect to time, this is how the voltage across the capacitor changes. Initially, the voltage across the capacitor is 0, and then with the passage of time, this voltage is increasing with respect to time, and this time is known as charging time. This charging time of the capacitor depends upon the time constant of this RC series circuit, and the time constant of this RC series circuit is Rc. And this capacitor usually takes 5 tau to 6 tau to be fully charged. So this is approximately the charging time of a capacitor. The charging time of a capacitor is approximately equal to 5 or 6 tau. So this is the charging current. Finally, the voltage across the capacitor will be equal to the source voltage. So after the charging period, the voltage across the capacitor will be equal to the source voltage. So this is the normal condition or the normal state. This normal state is also known as steady state condition. So this normal condition, the capacitor will behave like an open circuit for the DC voltage. There will be no current in this capacitor under normal or steady state condition. I am talking about this area. Let me consider the sketch once again. This is the charging period of the capacitor, and here is the steady state condition of the capacitor. Under steady state condition, the capacitor will block the DC current. There will be no flow of DC current in the capacitor during the steady state condition. During the analysis of the circuits, we do not consider the charging period because the charging period is very small. So we just consider the steady state condition of the circuit. Under steady state condition, we know that the capacitor will block the DC current. The voltage across the capacitor will be equal to the source voltage. So under steady state condition, the voltage across the capacitor will be equal to the source voltage. We multiply both sides of the last equation by C. So CVC will be equal to CVS into 1 minus e raised to power minus t by RC, and this equation can be written as, this is the equation for the charge on the plates of the capacitor. Initially there is no charge on the plates of the capacitor, then the charge on the plates of the capacitor increases exponentially with respect to time, and finally the charge on the plates of the capacitor is constant, that will be equal to Q. So under steady state condition, the charge on the plates of the capacitor will be equal to capital Q. We sketch the charge with respect to time. So if you sketch the charge with respect to time, initially the charge on the plates of the capacitor is 0, and then it increases exponentially with respect to time, and finally the charge on the plates of the capacitor becomes constant, which will be equal to Q. So capital Q, which is the constant charge on the plates of the capacitor, is equal to CVS. This will be the charge on the plates of the capacitor under steady state condition or normal condition. Now we differentiate this equation with respect to time to find out the equation for the time varying charging current in this particular circuit. So we differentiate this particular equation, and the integration of this equation gives you dq by dt, which is equal to Vs by R into e raised to power minus t by RC, and this is the equation for the charging current in this series combination. You see, the equation for the charging current is a function of time. So this is a time varying current. The current varies with respect to time. This is what we assumed initially during the analysis of this particular circuit. We assumed that the charging current is a time varying current, and we have proved that the charging current is a time varying current. So the charging current is a time varying current. At time t is equal to 0, the current in the circuit will be maximum, and the maximum value of the current will be equal to Vs by R, and then this current decreases exponentially with respect to time, and finally this current will become equal to 0 after some time. So initially the charging current in the capacitor is maximum, then this current decreases with respect to time, and finally this current becomes equal to 0. So the current in this circuit will be 0 under normal condition or under steady state condition. Now let us consider the discharging of the capacitor. So we have connected the source across the RC series combination, and we consider this particular circuit under steady state condition. We know that under steady state condition there will be no current in this particular circuit, and the voltage across the capacitor will be equal to the source voltage. So we consider this particular circuit under normal condition or under steady state condition. We have applied the DC voltage source across this RC series combination. The capacitor has been charged up to the source voltage. There is no further flow of DC current in this particular circuit. So the DC current in the circuit is 0. The voltage across the resistor is 0, and the circuit is under normal condition. The voltage across the capacitor is equal to the source voltage. Similarly, the charge on the plates of the capacitor under steady state condition will be equal to capital Q, and the voltage across the capacitor under steady state condition is equal to the source voltage. Now what we do, we move the switch to this particular position. What we do with the help of this particular switch, that we disconnect the source from the RC series combination. So we move the switch of this particular circuit at time t is equal to 0. So as we move the switch at time t is equal to 0, the voltage across the capacitor will be equal to Vs. This is the initial condition for the circuit now, that during the switching process, the voltage across the capacitor is equal to the source voltage, and the charge on the plates of the capacitor is equal to capital Q. So we disconnect the source from the circuit at time t is equal to 0. Look at this particular circuit. We have disconnected the source from this particular circuit. So we assume that there will be a discharging current in the capacitor, and this discharging current will develop some voltage drop across the resistor as well. We assume that this is the direction of the discharging current. We do not change the direction of the discharging current in this particular loop. We assume that the discharging current is in the same direction. We will derive the equation for the discharging current. If the equation for the discharging current is positive, then the assumed direction will be okay. And if there is a minus sign with the equation of the discharging current, then this assumption will be wrong, and the discharging current will be in the opposite direction. So anyhow, we disconnect the source from the RC series circuit, and there will be a discharging current in this RC series circuit now. This discharging current in this RC series circuit will be for a very small interval of time, and this small interval of time depends upon the time constant of the circuit, where the time constant is equal to RC. So the capacitor will be discharged in 5 tau or 6 seconds. This much time is approximately taken by the capacitor during the discharging period. Anyhow, we apply KVL to this particular loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. If you look at the direction of the current, there is no voltage rise in the loop. There are two voltage drops. The voltage across the resistor is a voltage drop, and the voltage across the capacitor is a voltage drop. So according to KVL, there is no voltage rise in this particular loop. So the voltage rise in this particular loop is 0, and the voltage across the resistor is a voltage drop, and the voltage across the capacitor is a voltage drop. VR will be equal to IR. Now I represents the discharging current. It represents the discharging current in the capacitor now. So we put the value of VR in this particular equation, and we obtain this particular equation now. 0 will be equal to IR plus VC. You see, this is a series loop, so the same current flows in the capacitor as well as in the resistor. If this current flows in the capacitor as well, then we know how to find out the current in a capacitor. The current in the capacitor will be equal to C dVc by dt, and we put this value of the current in this particular equation. 0 is equal to IR plus VC. So we put the value of the current in this particular equation, and we obtain this particular equation, that is 0 is equal to RC into dVc by dt plus Vc. Now what we do, we rearrange this last equation of this particular slide. So let us rearrange it. So we rearrange this particular equation. The rearrangement of this equation gives you dVc by Vc, which is equal to minus dt by RC. We integrate both sides of this equation, that is the integration of dVc by Vc and the integration of minus dt by RC. The integration of left hand side results in log of Vc, while the integration of the right hand side results in minus t by RC plus k, where k is the constant of integration, and we need to find out this constant of integration with the help of initial condition. What is the initial condition for this particular circuit? This is the initial condition. At time t is equal to 0, I moved the switch of this particular circuit to another state, to another position, and at that particular instant the voltage across the capacitor was equal to the source voltage. This is the initial condition for this particular circuit. We put this initial condition over here in this particular equation. So let us put the initial condition over here to find out the constant of integration. So k comes out to be log of Vs, and then we put the value of k over there. So log of Vc minus t by Rc, log of Vc will be equal to minus t by Rc plus log of Vs. The same equation can be written as log of Vc by Vs, which is equal to minus t by Rc, and we take anti-logarithm on both sides of this particular equation. So anti-logarithm on both sides of this equation results in Vc by Vs, which is equal to E minus t by Rc, and Vc will be equal to Vs into E minus t by Rc. This is how the voltage across the capacitor will decrease with respect to time. During the discharging process, initially there is a maximum voltage across the capacitor which is equal to the source voltage. Then during this discharging process, the voltage across the capacitor will decrease, and the voltage across the resistor will decrease as well. So if we sketch the voltage across the capacitor with respect to time, this is the sketch for the voltage across the capacitor. Initially, the voltage across the capacitor is maximum at time t is equal to 0, that is equal to the source voltage. Then the voltage across the capacitor decreases exponentially with respect to time. Finally, this voltage will be equal to 0. We multiply both sides of the equation for the voltage across the capacitor by C, and we get the equation for the charge. So the charge on the plates of the capacitor is a function of time, and this charge will be equal to CVS into e raised to power minus t by RC. And this equation number 89 of my personal book reveals that the plates that the charge on the plates of the capacitor will decrease exponentially with respect to time. So if we sketch the charge with respect to time, the charge on the plates of the capacitor will decrease exponentially with respect to time. Initially, the charge will be maximum, which is equal to Q. So the maximum value of the charge at time t is equal to 0 on the plates of the capacitor will be equal to CVS. Then this charge will decrease with respect to time, and finally this charge will be equal to 0. What we do, we differentiate the last equation of this particular slide with respect to time. We differentiate both sides of this equation with respect to time to find out the equation for the discharging current. So if we differentiate both sides of the equation for the charge with respect to time, we get dq by dt, which is equal to minus Vs by R into e raised to power minus t by Rc. This is the equation for the discharging current. So the discharging current will be equal to minus Vs by R into e raised to power minus T by RC. So we have minus Vs by R into e raised to power minus T by RC. There is a minus sign with this particular current, which indicates that this current is in the opposite direction. The assumed direction of the current is wrong. We sketch the discharging current with respect to time. So initially the discharging current is maximum in this particular circuit. Then with the passage of time, this discharging current decreases with respect to time. Let us do a few numerical example. There is a capacitor of 20 microfarad, which is charged to a potential difference of 400 volt and then discharged through a 100 kilo ohm resistor. Calculate the time constant, initial value of discharging current and voltage across the capacitor, and voltage across the capacitor after 2 seconds. So anyhow, we know that the time constant of this RC series circuit will be equal to RC, which is 2 seconds. This is the equation for the discharging current. The discharging current will be equal to Vs by R into e raised to power minus T by RC, and the initial value of the discharging current will be maximum, which is equal to Vs by R. Excuse me. So we calculate the initial value of the discharging current. Vs is 400 volt, the resistance is 100 kilo ohm, so the initial value of the discharging current is 4 milliampere. So then we calculate the voltage after 2 seconds. So the voltage across the capacitor is equal to Vs into e raised to power minus T by RC. After 2 seconds, the voltage across the capacitor will be equal to Vs into e raised to power minus 1. We put the values over here in this particular equation. Vc will be equal to 400 into e raised to power minus 1, and the voltage across the capacitor after 2 seconds will be 147.15 volt. We do another numerical example. This is example number 1.10 of my personal book. Please purchase the book because I'm giving you the homework. As a homework, you guys will have to solve all the 4 questions of the exercise of this particular chapter, and all these questions are given in the exercise of my personal book. So please do all the 4 questions of the exercise of my personal book and submit it to me as soon as possible. So there is an 8 microfarad capacitor which is charged to a potential difference of 200 volt through a series 0.5 mega ohm resistor. Calculate the time constant. We know that the time constant will be equal to RC, initial value of charging current, current in the capacitor after 4 seconds, voltage across the capacitor after 4 seconds, and the time taken by the for the potential difference across the capacitor to grow to 160 volt. We solve this numerical example. We know that the time constant is equal to RC, which is 4 seconds. So the time constant of this particular circuit is 4 seconds. So if you guys want to charge this particular capacitor, you guys can charge this particular capacitor approximately in 20 to 24 seconds. Well, the current in the capacitor is given by this particular equation. We have Vs by R into e raised to power minus T by RC. Initially, there will be a maximum current in the circuit at time t is equal to 0. So this is the initial value of the current, which is maximum. The maximum value of the current is Vs by R. So if we put the values, we get the maximum value of the initial current, which is 400 microampere. Well, we calculate the current after 4 seconds. So we just put the values over here, and the current in the circuit after 4 seconds is 147.15 microampere. So the initial value of the current is 400 microampere, and this current drops to 147.15 microampere after 4 seconds. Now the voltage across the capacitor after 4 seconds, we know that the voltage across the capacitor will be equal to Vs into 1 minus E raised to power minus T by RC. We put the values in this particular equation. So Vc will be equal to 200 into 1 minus E raised to power minus 1, and the voltage across the capacitor is 126.4 volt. We do the last part of this particular question. We need to calculate the time in the last part of this particular question. We consider the equation for the voltage across the capacitor, which is an instantaneous equation, which is the equation for the time varying voltage across the capacitor. Vc will be equal to Vs into 1 minus E raised to power minus T by Rc. The voltage across the capacitor is known, which is 160. The voltage across the source is known, which is 200. And T, Rc in this particular case is known, which is 4. T is unknown. We need to calculate T in this particular equation. So we simplify this equation. We get E raised to power minus T by 4, which is 0.2. And we calculate log on both sides of this equation. So we have minus T by 4, which is equal to log of 0.2. And if we simplify this particular equation, the time comes out to be 6.44 seconds. So after 6.44 seconds, the voltage across the capacitor will be 160 volts. Please do all the 4 questions of the exercise of my personal book. Thank you so much.